Hello students, welcome to EPG Pathshala. I am Dr. Mamuna Akhtar from School of Pharmacy Education and Research, Jamia Hamdard. Here we are going to discuss about the module Factors Affecting Fluorescence and Phosphorescence from paper Atomic Absorption Spectroscopy. So students, let's see what we are going to learn in this module. First, we'll brush up the concept of fluorescence and phosphorescence, the factors that affect the fluorescence and phosphorescence, the source of light, concentration of the inner light, which can affect the intensity of fluorescence, the importance of transition types, structure, and its rigidity. We also will discuss the importance of solvent, pH of the solution, and temperature with respect to fluorescence and phosphorescence. So we already know about fluorescence by now. So fluorescence is an emission spectra. And this emission spectra provides information for qualitative and quantitative analysis of substances, and this is called molecular luminescence procedures. So luminescence is most conveniently defined as the radiation emitted by a molecule or an atom after it has absorbed energy and gone to the excited state. The two types of luminescence procedures are determination of fluorescence and phosphorescence. The two phenomena are often referred as photoluminescence, and the difference between the two is very small, but the impact is very large. The phosphorescence involves change in spin of the excited electron, whereas fluorescence does not involve any change in spin of the excited electron. We already know that fluorescence is short-lived, with luminescence ceasing almost immediately. That means as soon as the incident light is cut off from the substance, it stops to emit light. In contrast, phosphorescence remains for easily detectable time after termination of irradiation. That means even after the incident light is cut, the substance shows emission or fluorescence. In most instances, photoluminescence is longer in wavelength than the radiation that is used for its excitation. Theory of fluorescence and phosphorescence in brief. We know molecules have molecular orbitals that hold the molecules bound together. Atoms have atomic orbitals that determine the energy levels of the electrons. So when an atom or molecule is exposed to light, the absorption of light results in electronic transition. In atoms, the transition involves the promotion of electron from an outer shell orbital to an empty orbital of higher energy. Whereas in molecules, the electron is promoted from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. There are some terms which are used in fluorescence, phosphorescence, and which we should refresh again. Singlet excited state, one of the electron is excited from the ground state and the spin is not changed. Excitation is moving of electron to higher level after the atom has absorbed or molecule has absorbed energy. Decay, deactivation, or relaxation. It is the process of returning to ground state by the release of excess of energy. It can be by any method, release of energy by collision, by heat, or by emission. Emission is the release of absorbed energy in the form of a photon. Fluorescence is the emission of photon from a singlet excited state to a singlet ground state, or between any two energy levels with the same spin. Average lifetime of the electron in the excited state is only 10 to the power minus 5 to minus 8 seconds. So fluorescence decays rapidly after the excitation source is removed. Phosphorescence. Phosphorescence is a state of singlet excited state that has transformed to a triplet excited state. That is, the spin of the paired electrons is no longer paired and one of the electron has changed its spin. The radiative process originating from the triplet state takes time because inversion of spin of one of the electron when it moves from the lowest unoccupied molecular orbit to the half-filled highest occupied molecular orbit is forbidden process. This is according to the Pauli's exclusion rule, according to which no two electrons can have same spin in the same orbital. So according to this, an electron which has changed its spin cannot come to the ground state as such. So it occurs on a time scale much longer than the fluorescence process, and the average lifetime ranges from 10 to the power minus 4 to 10 to the power 4 seconds. And the process is called phosphorescence. Phosphorescence therefore continues even after removing the excitation source. This figure shows you the process of transition of electrons from ground level to the next higher level that is available and change of spin. So A is the singlet ground state where two electrons with opposite spin are in the lowest occupied orbital available. And B is the singlet excited state whereby a molecule or atom has absorbed energy and one of the electron goes into the next higher level available with no change in spin of electron. And the third state is triplet state, where the electron after absorbing and moving into higher level has changed its spin. The process of fluorescence. Fluorescence can occur in simple as well as in complex gaseous, liquid, and solid chemical systems. The simplest example is a vaporized sodium atom, where the molecule of sodium absorbs energy and the electron from 3s is excited to 3p by absorption of wavelength of 5896 angstroms and 58960 angstroms. Immediately after the source of light is stopped, the electron returns back to its ground level by radiating or emitting photons of same two wavelengths. This only happens within 10 to the power minus 5 to minus 8 seconds. Such a phenomena is known as resonance fluorescence. This fluorescence and phosphorescence is the ratio of the number of molecules that luminescence to the total number of excited molecules. Because it's not always that the number of molecules which excite all will fluoresce. For highly fluorescent molecules such as fluorescein, the ratio approaches to unity. By now, we are very well versed about the fluorescence and phosphorescence. Now, before taking anything into consideration, we need to know the factors that will affect them. So, in case of fluorescence and phosphorescence, there are a number of factors which can affect. There are two types of factors. One is intrinsic structure of the molecule, that means factors which are due to the intrinsic properties of the molecule, which arise from the structure of molecule. And second is extrinsic factors, that is which arise due to the environment of the molecule. In a way, you can say when you take fluorescence, when you record fluorescence in solution becomes the external environment. So intrinsic structure of molecule and factors which depend upon it are transition type in fluorescence, quantum yield or efficiency, structure of a molecule which fluoresces, structure rigidity. And extrinsic or environmental factors include the light source, which are other than the molecule which shows fluorescence, the concentration, temperature, solvent effect, effect of pH of solution, effect of dissolved oxygen. Transition type in fluorescence. So type of transition is very important when it comes to the intrinsic factors involved for fluorescence. Fluorescence is only possible in molecules which have conjugated pi systems. And as we know, fluorescence is commonly produced from a transition from the first excited electronic state to one of the ground vibrational state. It is generally produced by transitions involving pi to pi antibonding or sometimes from n to pi antibonding. The molar absorptivity of pi to pi antibonding transition is 100 to 10,000 folds greater than non-bonding to pi antibonding transition. The inherent lifetime associated with pi to pi antibonding is shorter, 10 to the power minus 7 to 10 to the power minus 9 seconds, compared to the non-bonding to pi antibonding, which is 10 to the power minus 5 to 10 to the power minus second, that is lower than the pi-to-pi antibonding, and fluorescence is large because less time for deactivation is available. Quantum yield or quantum efficiency. Quantum yield is the ratio of molecules that fluoresce to the total number of excited molecules. So it indicates that not all the molecules that excite show fluorescence. For highly fluorescent molecules, the quantum efficiency approaches unity under the same conditions. An example of such a compound is fluorine. Molecules which do not show fluorescence have quantum efficiency that approaches to zero. Quantum efficiency is denoted by phi and is determined by rate constants for the process by which lowest excited singlet state is deactivated. Since we have already discussed various factors which deactivate the process of fluorescence, like fluorescent, internal conversion, external conversion, intersystem crossing, pre-dissociation, and dissociation. The equation above permits the quantitative interpretation of the structural and environmental factors which affect the fluorescence, like K fluorescence, K pre-dissociation, and K dissociation are mainly dependent on the structure of the molecule, whereas others are dependent on the environment. The relative fluorescence quantum yield can be determined experimentally by measuring the fluorescence of fluorophore of known quantum yield with the same experimental parameters, that is, the wavelength used for excitation, the silt width, photomultiplier used as a detector, voltage, etc., as the substance under test. This equation can be used to calculate the relative fluorescence quantum yield, where phi is quantum yield, INT is the area under the emission peak, A is absorbance, also called optical density at the excitation wavelength, N is the refractive index of the solvent, and subscript R denotes the respective value of the reference substance. The effect of structure on fluorescence. We know fluorescence is due to the presence of conjugated pi system. Therefore, all aromatic compounds should show fluorescence, and which actually happens. Most of the compounds that contain aromatic functional group have pi-to-pi transition, therefore are active in fluorescence. Aliphatic compounds or alicyclic compounds which have high conjugated system also show fluorescence. The quantum yield increases with the number of rings increases, conjugation increases, their number of degree of condensation increases. Heterocyclic compounds have lowest energy electronic transition levels because heterocyclic compounds have heteroatoms. Heteroatom means presence of non-bonding electrons, so they will show a transition from non-bonding to pi antibonding, and that rapidly converts to the triplet state. So therefore, fluorescence decreases, phosphorescence increases. For example, pyridine, furan, thiophene. There are some other compounds which contain fused benzene nucleus, they show fluorescence. So you can have same heterocyclic compounds fused with benzene, they have fluorescence. For example, quinoline, isoquinoline, indole. Fluorescence has also been observed to decrease if the substitution containing is heavy, or you can say halogen, for example, because of heavy atom effect that again enhances intersystem crossing, results in phosphorescence and diminishing of fluorescence. Substitutions like carboxylic or carbonyl group, they also cause decrease in fluorescence due to N to pi transition. The nature of group attached to the aromatic nucleus also has effect on the fluorescence of the substance. For example, electron donating groups increase fluorescence because they delocalize the pi electrons and tend to increase the probability of transition between the lowest excited singlet state and the ground state. For example, groups like amino group, hydroxyl group, methoxy, ethoxy group, cyano group, secondary amine, tertiary amine, or nitro group. In contrast, groups which have withdrawing effect, that which withdraw the electron density towards them, they decrease the fluorescence intensity. For example, carboxylic group, aldehydes, ketones, thio group, and heavy atoms, fluorine, bromine, chlorine, iodine. There are some groups which do not affect fluorescence. That means they do not enhance nor they adversely affect the fluorescence, like sulfonic acid group, tertiary amine, alkyl groups. Structure rigidity has also affected the fluorescence of the substance. It has been observed that planar the molecule, the fluorescence will be high. In a way, you can say non-planar molecules usually have structural less absorption and fluorescence spectra. Planar and rigid molecules have high symmetry, therefore fluorescence. Transition from planar and rigid molecules show increased quantum yield compared to non-planar molecules. The reason for this may be that there is the good mixing of pi clouds due to the planarity of the structure. And very good example of this is biphenyl and fluorine. The structure of biphenyl is made rigid by simple introduction of methylene group. The two phenyl rings in biphenyl are perpendicular to each other, whereas in fluorine they are all in same plane. In biphenyl there is no thorough mixing of the pi clouds of the two phenyl ring, whereas there is good mixing of pi clouds in fluorine, thereby increasing the chances of fluorescence. It is believed that the ability of some molecules to emit fluorescence radiation is only due to their molecular rigidity. However, scientists have shown that it is not the rigidity of the singlet state which is important for a molecule to show fluorescence. It is also important to show rigidity in the first excited singlet state. Maintaining a planar or near planar configuration in singlet excited state helps in showing the fluorescence nature. However, there is no doubt about the fact that planarity and rigidity of the molecule plays important role in determining the fluorescence parameter of a compound. So here is an example of planarity and rigidity of the molecules and their fluorescence. We can see compound number 1 has quantum yield of 0.17, and as you increase the rigidity, the quantum yield increases. Similarly, from compound number 5, where the quantum yield is 0.8, the rigidity increases, the fluorescence of the compound increases. The rigidity of compounds also happen due to the complexation with some metals. For example, in case of 8-hydroxyquinoline, if its complex is made with a zinc, the fluorescence is increased. Another example is complexation of diethylamine and N-methylpiperazine derivative with nickel, copper, and zinc. And in all the cases, the complexation has improved the emission. After discussing the intrinsic factors, the extrinsic factor involves the light source. The light source is the source of light which is used to excite the electron in the system. The source of light with appropriate wavelength is very much important in excitation of the electron from its lowest occupied level to the excited state. The use of light source that has a relatively higher intensity is desirable. For example, mercury lamp can be used as it produces satisfactory spectral range around 253.7, 302.2, 313.2, 435.8, 546.1 nanometers. The continuum lamp like deuterium and quartz iodine source have too low intensity. As a result, fluorescence intensity will also be low because it is the amount of energy you supply, you will receive the same amount of energy in emission. So therefore, it is important that you have a light source which has high intensity. Most fluorescence spectrometers use high pressure xenon arc lamp. It produces high intensity continuum light spectrum from 200 nanometers to 1000 nanometers. That means most of the visible range is covered in there. These lamps are designated according to the electrical power consumed. That means the amount of wattage used. It can be 150 watt, it can be 450 watt or 1000 watt lamp. In instruments, 75 watt xenon arc lamp has also been used, but it's pulsed so that the peak intensity of each pulse is high. So in addition, both molecular and chemical environment determines whether substance will or will not fluorescence. That means even if you provide a high intensity for excitation of a molecule, other factors also affect the emission of the system. After light source being an extrinsic factor which affects the fluorescence, is a direct factor which affects the fluorescence of the molecule. The power of the fluorescence radiation is proportional to the radiant power of the excitation beam that is absorbed by the system and is given by the expression F is equal to Kc. According to equation, the fluorescence is directly related to the concentration, but as we have discussed earlier, it does not hold true for concentrated solution. There are deviations. This slide will show you the effect of concentration on fluorescence. So the left side graph shows you concentration versus fluorescence spectra of a dilute solution, and in contrast, right hand side graph shows you the fluorescence spectra of a substance concentrated solution to fluorescence. The left side graph is straight, whereas the right side graph bends towards the or is parallel to the concentration. So we can say deviation at higher concentration from normal may be due to the self-quenching or self-absorption. Another important factor that is responsible for change in fluorescence is temperature. Quantum yield decreases with increase in temperature. We say quantum yield is ratio of the molecules that fluoresce to the number of the molecules that excite. So if anything that results in decrease in the energy of the excited molecules will result or will affect the fluorescence of the substance. So temperature is one such factor, because increase in temperature means increase in collision, and when collision increases, that means energy is lost as a result of heat. So this will deactivate the process of fluorescence. This can be also seen when you change the viscosity of the solvent. So by decreasing the viscosity of solvent, it also leads to external conversion and have same effect as increase in temperature. External conversion means loss of energy due to collision. So this can be explained by the example of study of fluorescence of xanthine dye rhodamine B study in water using cuvettes and different temperatures. So this slide shows you emission spectra of rhodamine B in water from temperature 5 degree to 80 degree. You can see there is a gradual decrease in fluorescence with increase in temperature. It means temperature dependent change of rhodamine B. The temperature also affects the relative lifetime of the excited species. It can be seen in graph 2. Not only the viscosity of the solvent, but solvent polarity, dielectric constant, its polarizability also affects the fluorescence of a system. So change in solvent means change in everything. Viscosity, polarity, dielectric constant, change in polarizability. So thus the effect on fluorescence is expected. So with increase in solver polarity, both absorption and emission bands undergo bathochromic shift. The polarity of the solvent causes increase in non-bonding to pi antibonding transition, while pi to pi antibonding suffers opposite. For example, Coumarin laser dye C307 and C522B. A bathochromic shift in solvent with high polarity indicates the transition of pi to pi antibonding. This is the structure of Coumarin dye C307 and C522B. The fluorescence decreases by solvent containing heavy atoms like carbon tetrabromide and ethyl iodide, and this can be explained by earlier discussed factors, that is heavy atom effect. This graph shows you the effect of the solvent on the fluorescence of the Coumarin compounds. The absorption spectra of Coumarin 1 to 8 in chloroform at 10 to power minus 5 moles per cubic decimeter, and absorption spectra of Coumarin 1 to 8 in ppma at 0.002 moles per kg. In both the spectra, you can see the shift of absorption bands. So in addition to change in solvent, pH of the solvent also affects the fluorescein, because change in pH means change in the resonance structure of the compounds. So some compounds which can make resonating structures can have different resonating structures at different pH. So acidic and basic compounds respond to change in pH of the system. So both wavelength and intensity are different for the ionized and unionized form of the compound. This spectrum tells you about the effect of the pH on 7-hydroxycoumarin exhibits an intense blue or green fluorescence at wavelength of 460 nanometer below pH 2.2. The change in pH results in change in emission spectra. The graph is related to umbelliferon fluorescence spectrum as a function of pH. 7-hydroxycoumarin concentration 8 times 10 to power minus 7 molar, excitation wavelength 330 nanometers. The graph 1 is at pH 2.2, graph 2 is at pH 1.8, graph 3 is at pH 1.5, and graph 4 is at pH 1.2. So with change in pH, you can see the decrease in the intensity of the absorption. This is again an example of effect of pH of solution on emission spectra. So this is example of indole carboxylic acetic acid in aqueous solution. 3-indole acetic acid shows emission wavelength at 369, 378, 379 and 433 at pH of 1.2, 7, 12.5 and 5 normal NaOH. You can see the shift of wavelength from 369 to 433 with change in pH. Similarly, you can see 3-indole pyruvic acid. The emission at pH 1.2 is at 405.5, whereas it moves to 429 when the solution is very alkaline. In addition to the pH of the system, the presence of oxygen in solution also affects the intensity of the fluorescent substances. Dissolved oxygen causes decrease in emission intensity of fluorescent solution. This may be due to the photochemical oxidation of the fluorescent species, or it may be due to the paramagnetic properties of molecular oxygen. Due to this, intersystem crossing happens, that is conversion of excited molecule, excited singlet state to the triplet state. Excited singlet state is where the spin of the electron does not changes, whereas the triplet state is where the triplet spin of the electron changes. That means from fluorescence, the shift is to phosphorescence. There is loss of fluorescence and increase in the phosphorescence of the system. Halogens also result in decrease in fluorescence, and this decrease is due to an effect called heavy atom effect. It again results in intersystem crossing because the heavy atoms increase the probability of changing from singlet state to triplet state. Spin or orbital interactions become large in the presence of heavy atoms because the structure, or as you can see, the atomic number increases. The increase in atomic number causes increase in the size of the spin or orbital. So therefore there is interaction between the spin and the orbital. It results in change in the spin of the excited electron, therefore favorable for phosphorescence, and loss of fluorescence happens. So substituents like carboxylic acid or carbonyl group on aromatic ring also decreases the fluorescence. In these compounds, there is presence of non-bonding electrons, therefore the energy transition from non-bonding electron to the pi antibonding happens, which is less energy required, and therefore less of fluorescence is observed. Students, it's time to summarize what we have learned in this module. So we discussed about various factors after brushing up the fluorescence and phosphorescence concept. The factors that affect the process of fluorescence includes intrinsic properties of a molecule like its structure, rigidity, transition types, and in addition extrinsic factors like the source of light, concentration, its presence of the amount of substance, fluorescent substance, temperature, solvent effect, and the effect of pH of the solution and dissolved oxygen on the fluorescence of the fluorescing species. Thank you.